let's do free body diagram for a catapult. So a catapult, all your catapults are going to be built in kind of a similar way. There's a base. Of some sort. Whatever that is, might be a single popsicle stick, might be a wooden board, I don't know. And then you have the lever arm, which launches the projectile. Might be just another popsicle stick or a plastic spoon, doesn't really matter. And then most of you have something, some kind of fulcrum in here, like a stack of popsicle sticks or a bottle cap, or if it's smaller than some other kind of thing. And your catapult probably kind of works by bending back the lever arm, right? And loading potential energy into that lever arm. And then you have a projectile that sits on it and it's going to get launched, right? And that used to be here. I've made this dotted line so you can tell that's where it used to be. All right. So let's analyze the forces affecting the projectile itself, the thing we're launching. Let's say that we're launching a marble. What is one of the forces affecting that marble? Okay, it's going to have drag because it's moving through the air, absolutely. In which direction is the drag pointing? To the right? Yeah, to the right, because it's opposing. Remember, this marble's already, because we're launching it, it's moving through the air and it's experiencing a small amount of drag. And it's going to move in about this direction from where it used to be to where it is now, which is going to be basically at a right angle to your lever arm. So we can estimate that the drag is going to be in approximately the opposite direction from that. And it's a very minor force. We're talking about a very small projectile moving through the air, a very small amount of drag. So let's label that F subscript drag, force of drag. Okay, somebody else said gravity. Gravity points straight down toward the earth because the earth is what's making the gravity. So we'll label that grav, for force of gravity. And then we're missing one force, aren't we? Because if these were our only forces, that would mean that the marble's going to accelerate down and a little bit to the right. If we added these together to get our net force, the net force would be in this direction. But we know the marble's going to go kind of this way because of the force applied by the catapult. So let's just call it the applied force. The applied force is going to be in this general direction from where the marble used to be to where it is when it leaves the catapult, which is going to be at about a 90-degree angle from the lever arm of the catapult. So in this general direction. And let's just call that the applied force. APPL for applied. The applied force. Those are all the major forces affecting this projectile being launched from this catapult. So now, how do we get the net force? Let's start with a definition of net force. What does that mean? I'm going to write it up here. We'll write a definition for net force. Can someone help me out with that? Very good. Let's see if I can get one or two more answers from people hanging out. It doesn't have to be fancy scientific language. Just explain to me, what is net force? These wait times kill me. Angelina, I like your answer. So what do we do to get that value? Like what mathematical process? Yeah, Aiden, really good. Yep, absolutely. Yes, the net force is, it's the sum of all the forces acting on an object. And so because it's the sum, what does that mean? Well, it means we add them all together. Now here that's a little bit tricky because we have forces going at these diagonal angles. And so we'd have to do a little bit of trigonometry, this special mathematics that involves right triangles, to figure all of that out. It's not that hard to do, but can we make it simpler just to prove that we understand net force? Absolutely we can. Let's look at this in a very simple way. What is the strongest force affecting that marble in our diagram? What's the major force affecting it? The applied force. We know that because we draw these arrows with a specific length so that the longest arrow is the strongest force. And if it's a smaller force, we draw it with a shorter arrow. So if F applied, the applied force from the catapult is the strongest one, let's start there and say, all right, we'll start with a force that's that long pointing in that direction. Is there a force going approximately opposite the applied force? Yeah, the drag. So the drag points in the opposite direction. So when we add this many squares up and to the left, well, then we need to subtract from that this many squares down and to the right. So about that much. So we know that now the net force is a little bit smaller in magnitude than the applied force. Now we're missing one other force, the force of gravity. It's pointing down in kind of the opposite direction. So we need to pull this back and down a little bit. And our net force, when we add all these together, would be approximately right there. Approximately right there. So let's draw that on here to show that we can kind of visually estimate adding all these forces together. It's going to go that way, about that much. Okay, good. And that would be our net force. That would be our net force. Emma, yes, absolutely. Okay, do you have any questions about this catapult example? No. So what does the net force tell us now that we know in what direction the net force is and we know like how big the force is, what its magnitude is. What does it tell us? Now that we know the net force, what does that tell us about what that marble's going to do? Yeah, exactly, guys. It tells us something about the direction that marble's going to accelerate. It's going to go from having basically no velocity, and it's going to accelerate in this general direction. It's going to be accelerated in this moment, accelerated in that direction at the moment it leaves the catapult. And so we know it's not going to go exactly up in the direction of the applied force. Gravity is going to act on it a little bit. So it's going to accelerate in this general direction. Good.